Howdy, it's Mr. Russell. Let's talk about energy, specifically thermochemistry. It's in Chapter 6 on page 245. First, we need to get an understanding of all of our definitions. So, energy is the capacity to do work or to produce heat. Any matter will have some type of energy, from the hottest star to the coldest object you could think of, liquid helium or solid helium, is going to have some amount of energy. The first law of thermodynamics simply says that energy cannot be created or destroyed. It can be converted, but not created or destroyed. Since it's not created or destroyed, the total amount of energy in the entire universe is completely constant. Chemistry focuses on two different types of energy: potential energy, due to the position or composition, and the kinetic energy, due to the motion of the object. So kinetics means motion, so that's what we're talking about. Simply, it's shown by this girl dropping a ball. The ball has potential energy on the top, but when it is released, it gains speed, and so it gains energy as it falls and loses potential energy. The total amount of energy with the ball still remains constant. The physical definition of kinetic energy is 1/2 mass times velocity squared. So if mass is in kilograms and velocity is in meters per second, that means that if once you square meters per second, you get meters squared divided by second squared. This kilograms times meter squared divided by second squared just happens to be joules. So that's where the energy unit for joules comes from, is this derivation of units. Thankfully, this formula is provided on your formula chart for AP. So heat involves the transfer of the energy between two objects due to the temperature difference. So heat is the transfer of energy. Heat is really just involving transfer. There's that important distinction to make the difference between heat and energy. Those are two very different things. Work is defined as a force acting over a distance, and it involves the transfer of energy. Temperature is the property of the random motions of the molecules, so of the particles in that particular substance. So if the particles are moving slower, they have a lower temperature. But if they're moving faster, indicated by the longer arrows, then they have a higher temperature. Since they're moving faster, their velocity goes up, and that increases the kinetic energy. Remember, the 1/2 kinetic energy is 1/2 times mass times velocity squared. So that's what this is looking at. An exothermic reaction is a reaction that is releasing the heat. That means that the heat is flowing out of the system. Energy is traveling out. So as in a combustion reaction, which we have octane here, and it combusts with oxygen, and it creates carbon dioxide and water. So if a combustion reaction makes sense that it is an exothermic reaction. It will release some heat. So the heat that's released is now going to be signified by this 5,076 kilojoules. That is the heat right here. So this is still a balanced equation, but it's we're adding a certain little element to it by adding the energy to the equation as well. That's what we'll be doing in this chapter. Or we can write the normal equation here, and we can write delta H equals negative 5,076 kilojoules per mole. This is what's called the enthalpy. Delta H means enthalpy. And we'll get to that definition in a second. Delta H is going to be negative for an exothermic reaction. Always, 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 if delta H is negative, it is exothermic because the heat is leaving the system, so the system is actually losing energy. It's leaving the system. We can show a free energy diagram of the exothermic reaction when we have the reactants here, A plus B, and it is added some activation energy, some type of energy to increase it, and then start the reaction. Once the reaction has completed, it will now come down to the products, C. So this change between here and here is the change in energy. The change between the dotted line here and here. An endothermic reaction is something quite the opposite, where it is now absorbing heat. So now the system is taking in heat, and it is taking in energy. Since it is doing that, it is taking in these carbon and hydrogen are taking in some 52.3 kilojoules to make, is that acetylene? C2H4. I'm not sure if that's acetylene, don't quote me on that. But the heat term is on the left. That's the important thing. Is on an endothermic reaction, the heat term is on the left, and the delta H, or the enthalpy, is positive. There's no more correct answer for this. You could write it in the equation, or you could write this equation like normal and write delta H and then your enthalpy off to the side. Either one is perfectly fine. Again, just the same thing, where in a free energy diagram of an endothermic reaction, we have two reactants, A plus B, and they are now absorbing some heat until they get to a stable reaction here, which has, or stable product, which is C. So the space between these two dotted lines is the heat input. This little hump here can be different for every reaction, and so it's not really important to know the value of this this hump or this bump right here. You just need to know that the difference is between this line and this line. We'll have to get a good understanding of what our system and surroundings are. In chemistry, the system is our reaction, and the surroundings are everything else, whether it's the room, it's the floor, it's the desk, the outside air, everything else is the surroundings, but our system is what our reaction is actually taking place in. Taking notice of the diagram that I have here, where it's got our reaction in a nice little box, and then we're talking about the heat and workflow into the system here, and then you can draw an arrow for heat work out of the system. These boxes will help you really kind of visualize it. If you're really trying to figure a problem out, it's hard to keep it all straight in your head. Go ahead and try drawing these boxes with arrows. It gets a lot better. The internal energy is the sum of the kinetic and the potential energies of everything that's in that system. So here's the definition of enthalpy. Enthalpy is the internal energy plus the pressure times the volume. So the enthalpy is pressure and volume added into it. Right now in first semester, we're going to be thinking at constant pressure and constant volume. Did I say temperature before? Constant pressure, constant volume right now. And then later on, we'll try to account for different pressure and volume second semester. So the change in the enthalpy delta H is the energy flow as heat. So the H products minus the H reactants is going to be my delta H. So if my products were lower than my reactants, that would be an exothermic reaction, and you see how I get a negative delta H. That's where that comes from. Mathematically, we can show the internal energy by showing the heat and the work added together. Delta E is going to be the change in the system's internal energy. Q is heat, and W is work. E is almost always going to be in joules or kilojoules. Whenever we write these joules or kilojoules, it's important to put a sign on them. Whether or previously in your other math classes, you haven't had to put a positive next to it if it's a positive number, because positive is understood. It's not understood when it comes to energy. So I need you to put a plus sign or a negative sign if you need to. Just as a side note, the sign represents the system's point of view. But just as a side note, the engineers use the opposite point of view, so their signs are backwards. But that's really confusing, and we're not going to use it. So let's move on. The exothermic is going to have a negative Q, and endothermic has a positive Q. So here's where the box comes back. We have our box, which is our system, and here a positive Q, which means heat is flowing into the system. Okay? So that means that it is endothermic if it's going this way. And the work is also flowing into the system. So covering up that left side, I wish, here, I can do that. Covering up the left side and looking just at this, if I have my system, which is this box, the heat flows out of the system, which is a negative Q, and then work flows out of the system, which is a negative W. Remember that the energy is just the heat plus the work. So mathematically, let's do an example. Calculate delta E if Q equals negative 50 kilojoules and W equals positive 35 kilojoules. So delta E is just Q plus W. Just add them together. Negative 50 plus 35, and we get negative 15 kilojoules. Work can also be expressed through a gas that expands or is compressed by showing that work is a negative pressure times the change in volume, where the units are going to be liters times atmospheres. Let's do another mathematical example. If we calculate the work, if the volume of a gas is increased from 15 milliliters to 20 liters at a constant pressure of 1.5 atmospheres, the work is going to be negative P times delta V. So your delta V is going to be 1.985. That's because I had to convert milliliters to liters and then subtract the two of them. And find the difference. That's going to be my change in volume. My pressure is constant at 1.5 atmospheres, so when I dump that in the calculator, I get negative 3.0 liters times atmospheres. So like I said before, at the constant pressure, which is kind of where we're going to stay right now, the terms heat of reaction and change in enthalpy are used interchangeably. So delta H and the heat of the reaction are going to be the same thing. So now let's look at an actual reaction where we have sodium plus water yields sodium hydroxide plus hydrogen gas. The enthalpy is going to be negative 368 kilojoules per mole, so I know that's exothermic. Calculate the heat change that occurs when 3.5 grams of sodium reacts with excess water. Remember what excess water means? It just means that it's not the limiting reactant. So our limiting reactant is this one. So I know that I can use good stoichiometry by starting off with 3.5 grams of sodium. I will then convert my grams of sodium to moles of sodium from the periodic table. And it did give me the enthalpy in kilojoules per mole. So since it's in kilojoules per mole, my moles will cancel out. My grams will cancel out here. And since I have moles on top, I can put moles on bottom down here. When I do that, I need to be able to put the correct number of moles. Since there are 2 moles of sodium here, that's where this 2 comes from. That's where this one comes from, is this 2 from the coefficient of the equation. I don't have to worry about the sign when I do these stoichiometry calculations. It just means the heat is flowing out of the system. But actually, I do need to worry about the sign. I just left it out here. In my final answer, it still should be a negative 28 kilojoules. Thanks for watching, y'all.